He will talk on automated mathematical theorem proving, as you all can see on the screen. Thank you very much, Chen.
Yeah. Okay. Yes, thanks for the invitation from Liv and our colleagues in Russia. Today I'm going to talk about something about mathematical theorem proving. Just give you a brief introduction of myself. Okay, my background is informatics, and then spent several years in Huawei doing abstract interpretation. Interpretation when I'm doing my master's degree. After that, I moved to University of Nottingham to do the type theory, and algebra of programming for theorem proving. When I graduated, I got the PhD degree. I moved to Munich to do 1 year postdoc there, doing big abstraction. That's most favorite research in my career. That is a big abstraction. It's some kind of abstraction from big automata. Then I spent several years in University of Edinburgh doing formal methods and machine learning for security, especially for mobile security, how to use machine learning and formal methods to identify some security faults in mobile phones or applications. Okay, since the year before last year, I moved back to Huawei in Edinburgh to do these design automation and human reasoning things. Okay, so my research interests mainly on how to implement some formal verification methods more efficiently, maybe improving and design automation. Okay, so the group in Edinburgh is a very small theoretical group. We are focusing on the branch of math and engineering. The first topic, of course, will be the main topic of this year, maybe the year after this and next year. That's human reasoning, especially mathematical theorem proving. That's today's topic. And several other things we're investigating, including the matrix-based parallel computation for graphs and differential equations. That is saying, we think the matrix computation will become the interface, a common interface between applications and architectures in future. So almost everything, including machine learning, graph computing, and solving different equations, will be mapped to mapped to the matrix computation. Finally, okay. Another thing we have been investigating since 2019 is Aeronautics computational structures. That is about the floating point formats. When you design a new computation structure like adder, multiplier, you would like to know what's the error produced by this computation structure if you apply these structures on thousands or millions of numbers add or communication of them. Okay. The last thing is about design automation. We think one of the key points is equivalence checking in hardware design or software design is very important. Could be play the role of extraction and generalization from the legacy code or do some abstraction. Anyway, this is a background about me and the computation group in Edinburgh. So today's topic is about mathematical theorem proving. We try to understand the nature of human reasoning and try to figure out how human do the problem solving. Even when we're very young, we can solve the problem very quickly using known methods and tools, solve the problems we never met before. But how can people learn domain knowledge and produce conjectures and prove and disprove them? How can people develop new methods, even new systems to solve problems we can't solve using known methods and within known systems? This is something we want to understand. That's the nature of human reasoning and human problem-solving skills. So this is a very ambitious goal to do it. So, but in this research, we only have 1 year. So we will focus on the most creative part of human wisdom. We call it mathematical discovery and reasoning. So if you want to make progress, we want to build a theorem prover for human reasoning, actually. This quite long history since 1960 and 1970s. The first interactive theorem prover was developed, and a lot of automatic theorem prover. I guess most of you are very familiar with this area. A lot of theorem prover have been developed. However, not very certifiable. Some of them are very good. You can press a button, get a result. Some of them are very close to human readable, but it's still a lot of problem. We want to fill in the gap. This proposed theorem prover is can produce automatically human readable and machine checkable proofs. Hopefully, okay. It has a mechanism to explore the abstraction hidden in some structures, computational structures, so as to simplify the calculation and proofs. It also be able to generate conjectures from cases and even develop automatically some theorems from concepts and definitions. We hope we can do. Especially the second and third one will be the main innovations of this proposal, something different in scientific, in industry. Okay. So let's have a look at two examples. We would like to use two examples to show what we are going to achieve at the end of this year. The first example is actually on the automation of deduction systems. So try to prove these Diophantine equation. There doesn't exist natural numbers x, y, that, such that, blah, blah, blah. Okay, if we prove it as human beings, so how could we prove it? We ordinarily, okay, we can prove by contradiction to do the case analysis for different numbers. It could be odd number, even number for x and y, z, and produce some kind of contradiction. The main technology here is a proof strategy is infinite descent. Infinite descent actually is try to produce infinite sequences for such with list element. Because you can produce an infinite descent sequence and then descend in the sequence. And because this set has the list element, so there's a contradiction. You can say, something doesn't exist. It's impossible to do it. Okay. This proof strategies for human being will ordinarily just run. Yeah.
Sorry, 0 is not a natural number?
There is, here there is not natural number. We consider 1, starting from 1, okay. In mathematics, okay. In computer science, we consider 0 as a natural number, okay. Later, we'll consider 0 as a natural number, okay. So this outline of the proof strategy for human being. If we have looked at some proofs in books, you will see we call the proof sketch or proof outlines written in human language, natural language, describe this kind of proof strategies and the cases. Okay. But it's still, but to what extent a machine need to know about these proofs? For humans, we could understand and we could construct some proofs by ourselves, like some fundamental factors like the modular arithmetics and arithmetic on natural numbers. You don't need to care about it because well-educated mathematicians or computer scientists could understand what you mean. However, for machine, if you want the machines to do it, you have to teach the machines how to do this modular arithmetic and also very basic rules about arithmetic on natural numbers. Otherwise, the machine cannot understand your proofs. So this is the difference between human proofs and machine. We call it mechanical proofs. Mechanical proofs need a lot of details, and details may be not necessary for humans, but humans could reconstruct these mechanical proofs automatically. Okay, not really automatically by some efforts, but for machines, it has no this kind of ability. We want to develop this kind of ability as well. Okay. Another thing is about the hints actually, especially for here, the case analysis. How could the machine knows we need to do the case analysis on even number and odd number means the parities of them? Let's say why not just a prime number or some 4 times k, for example? Why is even number and odd number? But human can do this. Human will try to say even number and odd number, where it doesn't work. Could you get the contradiction? So this is part we call hints. It's quite hard to generate. I think it's the main difficulty in this problem. If you want to solve this problem, you have to ask the machines to do it automatically, to do the case analysis on the combinations of different parities. You can test different parities and see whether you can reach some kind of contradiction. Okay, this is first example. We would like to, the tool we have developed is try to take this as an input and output the whole proof for human to read and proofs for machine to check. Just machine checkable, human readable proofs. Okay. The second example, we will focus on induction. Consider this problem given by Polya. Actually, it's in 1945, and that is almost 70 years ago. Okay, consider the following tables and guess the general rules just by this example, then express it. For us, we know, okay, all the numbers on the left are just odd numbers, and there's some sequence there, there's a summation. And the right-hand side is the cube of n or something, okay. So if you could figure out this part, the left things is easier. The left thing, just a verification using mathematical induction to prove it, that's okay. But how to figure out these kind of things, ask a computer to do, we need some kind of capability called induction, okay, to generalize something or generalization from cases. Actually, this is another ability we want to develop here. Ask machines to do this kind of generalization and then do the verification automatically. We have no clear idea how to do it. Actually, probably we could do the enumeration of these expressions, possible expressions, some combinations of concepts, like different things, odd or even a prime number, maybe cube, maybe square, to test these against this number, just as we have done here. For human beings, we're looking for this, have a look at this number, see what its features or characteristic of these numbers, and find, oh, this is odd number, this is a cube of n something. When we test these numbers against, or cases against these concepts, we can produce the formulas quite like this one, the equation, the sigma here. Okay, when we have this equation, the left things will be automatic, we believe. Okay. So talk about the impacts of doing these project or something, including scientific and industrial. We would like to mention several things. One is it will enable the capability of answering complex queries for search engines, especially when you input something, questions to the search engine. The search engine could answer these complex questions, like solving problems, solving equations, and produce a closed formula for some progressions and prove it automatically, step by step. Another important application area is design automation. Huawei has a very big department to do software and very big department to do hardware as well. So there's a lot of requirements on software verification and hardware verification, or generation. Generation is better because the verification is just like reverse engineering, is harder than generation. If you generate something for specification, it's easier to then verify something has been implemented against some specification. Okay. So in design automation, we believe that the human knowledge will help finally things. Let's take example. If we verify some adder implemented in hardware, some kind of ripple carry adder, for example, and for this ripple carry adder, in order to verify it, we will convert them into propositional logic and feed it into such server to do the verification. It's called equivalence checking. There's example at the end of this talk in the appendix is about equivalence checking. Okay, in this problem, there's in this methodology, you will have the state explosion problem, scalability, and a lot of states. Okay, however, for human to do it, we will figure out some cutting points. We will say, oh, this is cascading, saying this 8-bit ripple carry adder. It will cascade 8 4 adder together and get this ripple carry adder. The cascading tells us there's cutting points will be very useful. We call them structures. These structures will be useful for accelerate this verification process, saying proof process. Okay. We hopefully we will the human proof of human skills will help identify these kind of cutting points to accelerate the process. This is a second application we call formal verification in hardware and software development. The third one might be interesting for machine learning people. In machine learning, there's a direction called neurosymbolic computation, to try to combine advantages from both worlds. One is from the neural world, another one is from the symbolic world. In symbolic world, things are quite explainable. We could understand why we get the result, do the reasoning. Maybe it's modus ponens, maybe it's a proof by contradiction, of course. In the neural network or neural computation world, it's not so obvious. Everything is embedded into some linear space or vectors, and you multiply these vectors. Okay, so definitely we need some kind of mapping. This mapping, maybe some homomorphism. We hope it will keep or preserve some properties of operations such that we can make use of advantage of both worlds. Okay. In symbolic world, I think something's good, like the reasoning is good, but in neural world, the pattern matching or pattern recognition, searching are quite good. But a lot of tasks we will see some examples later are not very suitable for neural or deep neural models to deal with. But some of them are good for them to do. Okay. Anyway, finally, this development will benefit the daily work of scientists, especially mathematicians, by providing friendly automated theorem provers. Okay. So in this talk, I will not. So our goal is not to develop a very generous automated theorem prover to solve all problems in mathematics and computer science. Okay. So, but we want to focus on how to automate as possible as we can some techniques in theorem proving. Okay. So we figure out several, I think seven techniques. Let's start from the evaluation and then do it one by one. For evaluation, what I mean is to manipulate expressions by applying the rules given in evaluation environment. Evaluation is the basis of all the other techniques will be used in computation, in proof, in calculation, in something else. Okay, so let's start with evaluation. Let's have a look at example. So basically, evaluation of an expression is trying to apply rules in the global environment until some condition is satisfied, or we stop the process. That's what we are doing, including human, including theorem provers, automated theorem provers as well. Okay. And so the expression here is very simple because we want to implement something. So we have to start from very concrete implementation details. So every typesetting forms here means it could be implemented. Okay, it has been implemented as well sometimes. Okay, expression is a variable or just a constant applying on variable. You can consider them as the syntax trees or the symbolic expressions raised by McCarthy in 1960s. So it is very simple to say we have some nodes, the internal nodes are just constants to apply some operations on the list of expressions. And for the leaves of the tree, the syntax tree, just variables, or sometimes it's just a list of empty list. Empty list means you don't apply anything. The constant is really constant in a set. The variable so could be replaced by any expression. This is a very basic syntax manipulation. We need it later. Okay. For
can I at this point ask
no
for clarification? So when you say that a variable or a constant is applying on expressions, what do you mean? You mean that complex expressions are built by application
yes,
of
exactly
of either constant function or a variable function, something like that?
So
your variables are functions, something like this, or
variable is not function. Variable is something could be replaced, and then a constant is a function. Could be a nullary function, binary function, or some anyway has some arity. Yeah. Okay. So you have a list of these expressions means the parameters for this function, the CST here. I'll give you an example. After that, you will get a clear idea of what's going on here for the expression. Okay. So let me do two more steps. One is about rule. Rule is just a pair of expressions. You can replace one side by another side. That is just equivalence relation in mathematics. Okay, or you can read it as some reduction order from left to right. We'll see several examples in different circumstances. It will have different meanings, but basically just a pair of expressions. Okay. The rule could be extended a little bit to get inference rule. The inference rule, the only difference is it has a local environment. I believe everyone who are familiar with inference rules or formal logic will get familiar with this. It's just the environment of it, the list of expressions we'll use. Some examples we'll give later. Okay. So now let's have a look at the first example. This example is very simple. Just say the rule here is associativity for addition. You just change the braces around the A and B and C. Okay. So when you have the expression here, expression variable here, A, B, C are variable, could be replaced by an expression. Let's consider first expression bottom. Here, U, V, X, Y, they are all variables, but plus is a constant. A constant is just the operation to apply on something. Okay, we just capture the structure. Okay, now we can do the matching. The matching things, a variable could match with any expression. So for this one, we just match A with U and B with V plus X is a sub-expression and C with Y. So this is very simple. You can generate, given an expression, arbitrary expression, given an arbitrary rule, you can match the left-hand side or right-hand side of the rule with expression, and all sub-expressions of this expression, and show all possible possibilities for people to choose which one you want to apply and get the result, and transfer or expression to another expression. This is second one. There's another matching that using the right-hand side with V plus X plus Y. That is another matching. You can do the expression. So this is very simple called substitution, raised by Naples. Naples, I think, anyway, 500, 400, maybe 400 years ago. Anyway, so it's just substitution equals for equals. That's the basic way we need to use in our proof. Okay. Then the inference rules. For inference rule, I'll give you an example here. Let us say we define a set. This set is a Boolean, just Boolean set. It's not necessary to define a true and false here in a formal system. Doesn't matter actually, but we declare them true and false here. You can use the different symbols to represent true or false, whatever, Boolean. And define a function called n function. Is n function defined by 3 rules. Of course, in some kind of functional programming language, we could use 2 rules to define it. There's some relation between these 2 rules. But here we would like to use 3 rules because we hope these rules are independent rules. So when you do the evaluation equation here, you can choose arbitrary one of the rules to apply, because they are equivalence relations. You can do replacement using the Leibniz rule, the substitution. And then here, I introduce 3 inference rules. The first one called assumption, just say, if you see something in the local environment, that means something in the assumption, of course, it's correct. Okay, if A is in assumption, then A is true. Okay. The second one is called the introduction rule for implication, saying if you want to prove A implies B, and we put A into the environment and prove B, that is called the introduction rule for. Anyway, it's also corresponding to application, or let me think, abstraction in number calculus. The third one is elimination. That is just a modus ponens. Say if I can prove A plus B, and I have proved A and then get B. Okay, this is inference rules. Just leaves the question: what is expression, and what is the rules and inference rules here? Okay, let's have a look at example here. We prove P implies P plus Q in plus Q. Okay, the first step is to put P into the local environment. And then put the P implies Q into the local environment. And then if you want to prove this, well, the next rule we will use is a LM rule. This elimination rule. For elimination rule, because you have 2 goals, for simplicity, we use n here, and it's the n function. To say for the left, we prove it's true. For the right, we prove it's true. Then we get the whole thing's true. Okay. For the left, because the assumption is true, the for right is true as well. So this is true. So this is evaluation. So give a demonstration also how to use this model, the evaluation model, to model everything, including proof, including calculation. The n function is a calculation, and computation as well. Computation is limited. Okay. So this is the first technology we use. This is naturally automatic. There's nothing to discuss more. Can implement it. And then the second one is called reduction. Reduction is just reduce the expression into its normal form. to be honest, what I mean here is just computation in lambda expressions or in rich lambda expressions. Let's go to the Church-Russell property to say, never mind about the order, evaluation strategy or order. You can always reduce the expression into its normal form. Okay, so sometimes the process might diverge. A simple example here, the natural number. Now, natural number is starting from 0. Okay, let's say the natural number is 0 or some kind of a function apply on natural number to get another natural number. This should be the injective function. Okay, this is a Piero postulations. Okay, it will be useful for induction. Well, when we apply inductions, we need this declaration in the front, say what's the natural number, how to construct natural number. For this construction, we can apply mathematical induction to do some proofs, but there's no other meanings or other useful in our system. For these types things we only need here, but for the rest of the part we don't really need types. We want to introduce types later, but for current stage we want to focus on a tiny small inference system without any typing. In future maybe we need it. Okay. Here I give examples, say how to do evaluation, to say whatever the evaluation strategies, you could evaluate 1 or 2 firstly, evaluate add firstly, but whatever, finally we'll get some normal form. The normal form is just 3 here, I think, 1, 2, 3, yeah. So this is computation. The whole process is automatic. There's no other choices. You can go to from one expression to the normal form. There are many passes, but for each pass, you will reach the normal form, whatever which pass you choose. So it's automatic, nothing to discuss. Okay, for some normal expressions, the process will not stop, will not terminate, it's diverge. Let's say the first one. First one is just a list of ones, infinite list. So if you evaluate it, you will get an infinite sequence. The second one is a fixed, that is a combinatorial logic called fixed point operator. Okay, it will call the function again. Finally, we'll call get an application function on some place. If you are familiar with lambda calculus, you know this is quite famous things there. Okay, whatever the process diverge or not, but there's a normal form. Normal form exists. For this case, nothing special to discuss as well. Even it doesn't terminate, we know the direction, we know how to evaluate it, so it's automatic. Okay. Then we meet something interesting called calculation. Calculation, what is calculation? Calculation here, for calculation, what I mean is some rules or some laws have been proved or are given by someone as axioms. Let's go back to the primary school. When we enter into the primary school, the teacher teaches us how to do the addition and the multiplication, and we know multiplication, addition are associativity law and commutativity law will hold, and then we can swap the numbers to do this addition by ourselves. Okay, for this case, we actually spend most of our time in school to learn a lot of rules and laws developed by other people, by physicians, by mathematicians, by a lot of people before 2000, long time. Okay, and then try to use it automatically, maybe just not just one, often several at one time. But for machine, it's a little bit hard to do this process. Let's see why. Okay. So let's have a look at the first one. This is just associativity and commutativity. If you compare the rules I have just listed on the screen, it's a little bit different from the rules I've given before. Saying here the rules for addition, there are 2 rules. You could say there's a reduction order. The structure on the left is more complex than the structure on the right. This is primitive recursion. Say m and n, one is suck n, another one is n. So n is simpler than left-hand side. So the first rule is the same. So we ordinarily do the evaluation, we will reduce from the left-hand side to the right-hand side. You will find the normal form. That's a straight. But for these 2 rules, different. Okay, if you see the structure, the structure doesn't change actually. Only the positions of these braces and positions for the for variables change. For the commutativity, you just swap the positions of these variables. For the associativity, you just change the braces or the structure of the expressions. But you cannot say, no one can tell you or which one is a normal form. It doesn't matter. Okay. So for when we do the proof, when we meet this kind of case, ordinarily we will find anyway automatically. If you want to do it automatically, we ordinarily will find some path from one expression to another expression. Here gives the example with the hash symbol in front to say, oh, this is not automatic, could be replaced by other rules to do this calculation. Okay. So in this case, we probably need a search process instead of the evaluation, automatic evaluation. This search process will help us to do better. Okay. So when I say main difficulty here, that means machine learning or statistical inference might help, or human skills might help. So how could human do this? Human will find some kind of mapping between these two, maybe some abstraction. I will mention abstraction later. Okay, to do this searching, to accelerate the searching, to avoid brute force searching in this process. If you do the brute force searching, it's always an NPC problem in computer science. So anyway, this is the first difficulty we will meet when we step into calculation instead of reduction. And the second one is sometimes a normal form might not exist. One of the
may I at this point also ask a clarifying question? So you had this evaluation, and you had so you had this reduction, and you had this calculation. So
yeah,
am I right in understanding it so that you speak about reduction when the rules are deterministic in some sense? So there is only one way to reduce a term.
Yes. Yes.
And
you have
calculation is that where you have really a non-deterministic search space for a non.
Exactly.
Okay.
Yes. Yes. Yeah. So basically, for computer science, we are working in reduction, just number calculus. Okay. For calculation,
but in number calculus, you also have non-deterministic,
exactly.
And reduce the term in different places, not in.
But you often have the normal form. But for the calculation, sometimes you don't have normal form.
Mm-hmm. Okay.
Okay. So you can diverge, lambda calculus diverge, no problem. Non-deterministic could be there, but it has a normal form. Always has normal form. Okay. But for calculation, sometimes there's no normal form. This example. So this is simplification of some trigonometric functions, and say this fraction of trigonometric functions. If you input the same thing into Mathematica, you will get 3 results. Okay, different results. Say, you have different. There are several rules actually. I think 10 rules. Maybe the basic rule just 2. One is Pythagoras, a squared plus b squared equals c squared. Another one is sine x plus y equal to sine x times cosine y plus sine y plus times cosine x. Anyway, so you have the basic rules, and you try to use these rules to simplify these trigonometric functions. Okay. According to different rules you are using, you will get different results. You can't say one is normal form, another one is not normal form. Even some of them are simpler than another one. Okay, like the second one is simpler than the first one, but maybe second one is easier to calculate in real case. Okay, so actually we don't know how to terminate for the evaluation. Sometimes it doesn't terminate, but we know the direction. Sometimes it will definitely terminate. But for this case, calculation, we just start from one point. The point is the fraction on the left-hand side. For the right-hand side, have no idea where we should go and what's the termination condition. Okay, so for this case, machines cannot decide which one they should stop and which form they should reach or which form they should go. Okay. For this case, I think that the human calculation patterns will help again. So if we anyway get a big collection of how human do this proof, do this calculation, do this simplification, and the machines could learn from this knowledge and try to do the simplification as human to mimic humans' calculation. Okay, this is the second difficulty, and the difference, also the difference between calculation and evaluation. Okay, let's go a little bit step further to inference. The inference is the main topic of today's main topic, actually. So the inference is a bit harder than reduction, but seems that it's simpler than calculation. Let's say why. Okay, so inference here, what we mean is to try to apply some inference rules or tactics to do the formal logic instead of syntax assignment or the index the semantics function to do the semantics function, to the evaluation or interpretation. Also, it's different from the automated theorem prover using resolution technologies. I will mention that revolution later, but for this one specifically, I mean Edinburgh LCF style. That is logic for computational function style. That is main technology used by modern interactive theorem provers. Okay. So the whole process is try to apply tactics automatically. So sometimes it's not automatic by human beings, sometimes given the tactics, and find the suitable parameters for these tactics and try to get to the proof tree. Let's have an example. This one, I give two tactics here. One is split. Say if you want to prove A and B, and you want to prove A and then prove B. And for destruction, this one say if you have something in the local environment A and B, you can split it to say this is just an assumption in my local environment. Say A and B could be used as A or B in the environment. Okay. Well, I have the issue you are produce a proof tree. This one is to prove P and Q implies Q and P. Then the first one is to intro to put the P and Q into the local environment and do destruction and split to finish. Finally, you will get the empty tree here to say everything's done, is resolved. This is the LCF style, Edinburgh LCF style. It's used in Cork, in Lynn, in Hull. Anyway, follow this style. But we don't think this style is good. There are two drawbacks. One drawback is anyway, let's talk about this later. Finish this example. We have these proof style. We can do the proofs, but sometimes for the inference, it's not as good as semantics or assignment. Here is the example to show that. If we just, you have several ways to prove this as true, x as true is the left unit of x, okay, in the AND function. The first one is try to do the case analysis to replace x by true and false, do the assignment and the semantics. That's okay, you can prove it, it's true, but just one step, you can do it, okay. But for the second one, you will use this inference rules. Inference rules make people confused. Sometimes you don't know, it's not human readable. Let's have a look at it. So for the inference one, for when we want to prove something equal, what we are doing to say, we will prove left implies right, right implies left. We get two things to. I think something's wrong here, but anyway, yeah, nothing's wrong. Just using AND to put the two trees here. And then do the introduction to put something into the environment and prove it finally, to construct the whole trees. That's another way to do it, called inference. We call it inference. This is inference. Inference, we don't need to understand the semantics, just follow the rules, and this is automatic, sometimes automatic. But for this case, for each step, we need a human being to specify which rules are using. We will see this process will be automatic, okay. So let's talk about the inference, automatic of inference, especially in last year, the year before last year, 2019. There's several papers published by Google DeepMind. It's about how to use machine learning to automate this process, especially this process to construct the proof trees. Okay, for a specific theorem prover HOL, HOL, high order logic. What they are doing is try to learn from a lot of cases, proofs produced by humans or proof converted from automated improvers, to try to figure out for each step which rule we should use. For example, for the first step, we know the rule we need to use is intro, and for that tool, it will produce the probability for all the techniques available. Say which one has a higher probability, we'll apply it. Okay. but I think that direction is a little bit wrong. There are two drawbacks. One drawback is here our system is very simple. There's no types, but for the whole and for cork, there's types. This makes things sometimes type system will make things harder to do automation harder. This is one drawback. So if we go back to the tiny or simple without type system, probably we can achieve better automation. Okay. The second is to take this as a black box to put everything into a deep learning model, deep learning model, deep neural models, and say, oh, could you give me the answer? Could you tell me which one is better? Okay. For that case, I don't think it's a good way to go, and also the result is not good as well. They use 20% of all the proofs in the library as a testing data set, and finally within this 20%, only 56 and 62% has been proved automatically. But for the rest, they were used them as a training data set and also the validation set. Okay, but if we carefully look at all of these tactics, we will notice it's not so hard to automate most of these basic mechanical proofs. Okay, we'll have some example later. Let's go a little bit further to look at the automation of mathematical induction. Mathematical induction is considered maybe quite hard part to do the automation. For human, it's quite straightforward, but for machine, it's not so straightforward. We produce these proof in Leibniz proof style. It were very clear and human readable, saying we do the induction on the second variable n. And then evaluation here means, as we have mentioned before, this is an automatic process. It's try to do everything automatic as we can. Okay, here means reduction, but later it will be some calculation will be added using the rules. But generally, just using some rules in the library. If you have more and more rules in the library, the evaluation is more and more powerful. And here the proof is simple. Say, if I know I would do the induction on the second variable, then it's 2 steps, and for each step here, you could automatically generate the proof to finish. This is Leibniz style and more human readable. And if you want to do this in LCF style, it's quite like cork, or have a very strong cork flavor. In order to prove the level C.5, we have to prove C.2, C.3, C.4. That means 0 is a unit of n, and then some auxiliary function, auxiliary lemma. Anyway, I do not want to rate it because all of these, anyway, I produce it by myself manually. It's not completely cork consistent, but this is a LCF style. So saying human, it's not human readable, and also you need to produce something you don't need to produce. And what we can do is to try to optimize this as possible as we can. Say, let's get rid of these details, cover these details using these Leibniz style things. It's more clear. It's clear, and also a lot of things are covered and encapsulated in the automation. Here is called evaluation. For hypothesis, this is rewriting rule is easier. Okay, for inference, another difficulty thing is about these existence quantifier. Existence quantifier, you need to construct something. You need to construct a specific mathematical object or structure to satisfy some condition. Let's have a look at this proof. This proof is produced manually as well, but I think it will be easily to be optimized. So here we prove if n is even number, m is even number, then the multiplication of them is even number as well, using the inference rules we have seen before. Okay, this is LCF style. To move something into these local environment and to explain them by their definitions. The definitions will be written as rules as well. So what is even? Even is exist k such that 2k equals n or n equals okay, is a predicate. You can return them as an expression and put it into the list of these expressions in the environment. And then the next step is tricky to see there exists a case such that 4ab equals 2k. We ordinarily need to construct this k, but the things is just hidden here to say if you replace n and m by 2a and 2b, you will find that, okay, k is just a 2ab. This is a little bit searching, but not so as complex as calculation. So we believe this part could be automated as well. So if you carefully look at the difference between the equations, equality, both sides of the equality, this is the inference. Okay, so for this part, we think we could develop, actually we have developed some automated inference algorithm to do this. This very straightforward, not very complex. To say if you give a goal, what we'll try to do is to apply tactics, the ranking tactics. See, the tactics has been ranked. In the next slide, there's a table to rank these tactics. You just apply these tactics, rank tactics, you will do this mathematical induction automatically, or you can automate most of these inference proof things automatically. Okay. Yeah, here is a rank table. The rank table things are for some of them are very straightforward, like implication and or not. So you have no other choices. You're just using one of the tactics. It's okay. For exists and for all, quite similar. But for exists, as I mentioned before, it'll be tricky. You have to identify some interesting mathematical object in order to make things correct. And then for the equality or equation, a little bit complex. If it's same, okay. If a equals b, that's reflexivity, just assumption, finish. Okay. And if a equal to b, they are different on both sides. They are different. What we're doing is to decide whether it's reducible. If it's reducible, we use a reduction. Use a reduction to reduce it to the normal form and do something. If it's not reducible, or whether it's rewritable. Rewritable means there's some hypothesis in the local environment. We can use it. Let's directly use the rewritten rules or the hypothesis in the local environment. That's okay. If it's not reducible, not writable, what we should do? There are several choices. One is to do the induction. Okay. For example, before that, here, when we have looked at this one, the first rule we need to use is intro, and then do the induction. Which variable we should choose the induction is tricky. It's based on the rules. We could have looked at the rules. Say for the second one, it's easier, but for the first one, you will not make any progress because the reduction is done on the second one according to the definition here. Here there's a second n and 0 because you do reduction there. Okay. This is one of choices, but there's several other choices. But induction could be induction is a best choices we need to use here. And then maybe some destruction. Destruction means case analysis. To say sometimes we need to, but for this tactic we need a partition of all the numbers in natural numbers. To say maybe some even or odd, just partition of it. But human will supply this kind of partition or the parameters for this tactic. And if these two cannot work, the rest thing is some other tactic, maybe proved by contradiction or proved by infinite descent. Anyway, there are several strategies, but not too many. Okay, so the main difficulty here is try to find the right parameters for tactics, for exists, for destruction, for induction. So for which variable we do induction, what kind of cases, what kind of partition we will use to do the destruction or case analysis. So what kind of mathematical object we need to construct for the exists. But I don't think this is so hard. I believe 70% or more than 70% trivial, tedious proofs in theorem provers, what they are doing by human beings, are quite easily to be automized using very simple ranking of tactics, the kind of breadth for searching. Okay, so but there are some pitfalls we need to avoid. Infinite paths is one of them. Okay, still, this is a proof of induction proof, mathematical induction proof. If we list all the possibility of doing this proof, we'll get a graph like this one. The interesting part is on the second one is alpha entails H alpha. H alpha means you change something, you change to the constructor, apply the constructor to your goal to prove. Alpha is your assumption. Say we assume alpha and to prove H alpha. That's what we're doing. Okay. For machine, all of these all these array arrows means the possible or valid tactics a machine can apply on a goal. If you are presented the goal alpha entails H alpha to machine have several choices. One is E, another one is using mathematical induction to produce C and D. Another one is F. Okay, so the goal is try to identify a path. The path if there's no conjunction in the middle node, we mean either path is okay. But if there's a conjunction in the middle nodes, that means both paths need to be true. To be true, we mean you will finally resolve the goal to finish it to get the square there. Okay. But if you consider mathematical induction, the first time where you use mathematical is okay. But the second time, just after the alpha entail H alpha, we use mathematical induction, you will see there's an infinite loop, and you can produce this infinite. It's an infinite path, not infinite loop. Okay, infinite path to produce these H alpha. Put the H alpha, H square alpha to Hn alpha into the local environment again. We have to avoid this kind of infinite loop. Infinite path. Another one is infinite loop, like E here. When you go from E to the right-hand side, actually we're applying sort of a commutativity law or some other law, okay? And you will go back to your original point, and you anyway go to the infinite loop. Okay, these two pitfalls we need to avoid, especially for the mathematical induction, the infinite path. If you go to the infinite path, definitely you will not find a good tree. Okay. So what we're doing here is still just ranking to postpone the mathematical induction at the end. Okay, if we can solve something or prove something without using mathematical induction, let's avoid to use it. Okay, that's a anyway. Okay. This is inference, and then the next one is resolution. I think the resolution is, as you might know, is just proved by refutation. It's an automatic technique. There's nothing too much to discuss about it. It's well developed, sometimes more successful than inference in LCF style for a long time. But we believe it has been used in a lot of tools like set solver, SMT solver, logic programming, knowledge graphs, and something else, and influence checking also as well in the hardware and software verification to verify some verification conditions, for example. Okay. But the main problem is scalability, as I discussed before. There's a static explosion problem, saying when you convert everything into propositional logic and feed them into set solver, and it cannot solve it because the scalability is limited. It's just now the best is millions of variables, I think, and that 3 divided by Microsoft. Okay, I think from our point of view, how could we improve this? As I said before, we could identify some specific structures like cut points, cascading, or some 2 to 3, 3 to 2 compression. This is very popular in Ada when we design design arithmetic, computer arithmetic units or ALU, algorithmic logic units. We will use these techniques like compression techniques, cascading, or recursion. Okay. If we could identify these cut points or the cascading structures, human beings will identify it very easily, even we don't do it manually because they're too complex. There are so many details. Okay, but if we could identify these cut points or cascading structures, that will reduce the verification task from the complexity of NPC problem or combinatorial problems into divide and conquer problem. To say you divide it into small blocks, and then you verify things on blocks. That way exponential from exponential to polynomial. Okay, the complexity. So we believe the human skills will accelerate the process if we want to achieve something automation or efficiency. But how to embed these skills into the system such that the system can use it is a research problem. I have no idea. Okay, so until now, I raised the three things. One is calculation. In calculation, we need human skills. Maybe some machine learning technologies could help us to model the human skills to do this calculation or proof. The second is in the inference. In inference, I think the structure itself could be automated, could be optimized very easily. But for some parameters, suitable parameters like hints for exists or for mathematical induction, you need some tricky construction. For that part, I'm not sure whether machine learning can help, but definitely it can play some kind of role to embed something into vector space to accelerate the searching. The third one is about the resolution. I think the human skills can help to identify some specific points or structures. Okay, until now, I have discussed 1, 2, 3, 4, 5, 6, one of the bases and 4 main techniques in deduction system. In deduction system.
May I ask you at this point the following question? So you sort of juxtapose calculation and inference. However, as we all know, you can view inference as a particular kind of calculation, right? So it's also a terminal writing system. And so what's the principal differences between the two things, so that you think that the calculation...
Give you example to show it. When you do the proof, you ordinarily, let's take this example. You ordinarily know the goal. This is a goal. This is left and right. You want to prove they are equal. But in calculation, you don't know the right-hand side. You only know the left-hand side. You will calculate from one side to another side. Say, when you do the calculation, we start from this fraction. So the goal is try to simplify it, but you don't know which one you want to go to. But for the proof or inference, we definitely know, or we want to prove this one equal to this one. And then you know the left and the right, and you do the proof. So I think the inference is easier than the calculation. The calculation, sometimes you don't know where you should go. Okay. Right. So of course, this is not very strict division of all of these techniques, but it's from the point of view of engineering, saying if you want to implement them, what kind of difficulty, what kind of techniques we can use in this. But basically, for the deduction system, all the rules, all the techniques we have included here. Only one thing we haven't discussed is abstraction. So the abstraction, I list 2 innovations of this project. One is abstraction, another one is induction. For abstraction, I should say, for sometimes the people will simplify the process, the proof process, instead of searching for proof in a space. I will do mapping, map this problem into another space and try to solve the problem maybe easily in another space. Okay. But the question is how could we automatically construct these abstract domains is kind of a challenging problem. Let's have a look at example. Okay. This example is a symbolic addition. As we seen before, this is kind of proof. This is inference. We have known the first one, x plus y plus u plus v, and then we have another one is x plus u y plus v. We want to show they're equal. The only things we need is just addition, symbolic addition. Say, we know addition is associative and commutative. That's fine. We have no other rules. It's 2 rules. Try to show these 2 same. This is inference. This is not calculation. Calculation, we don't know the rest. Okay. And then now, for human being, let's talk about the machines, not human being. Okay. For machine, what we're doing is to say, let's try different rules for each step. For the first step, we might use associativity. For the second step, we might use commutativity. We try all of these. The breadth first searching, that's okay. finally you will get the pass from the first step to the last step. For short expressions, that's okay. But for longer expressions or expressions with something changed or the variables is replaced, it's harder for machine to do. Anyway, it has to do the brute force searching for machine. Okay. But human will not do this like the machine is doing to try different associativity chemistry. For human, we will notice, oh, x, y, uv forms a multiset. The multiset for the both equations are same. Then definitely there is a proof. Even I haven't showed the proof to you. I know there's proof saying we could map these expression from the trees to multisets or bags. Okay, let's have a look at anyway some shapes here. So what we're doing here are for the expression have different shapes. The trees have a lot of shapes. This is cardinal number. If you count how many shapes are there for a specific n, is cardinal number. Okay, and then the 0, 1, 2 here, just encoding of the possible possible variables for this specific case. Possible variables on these on the leaves of the trees. Okay, you will notice that there are 1, 2. They have different sequences, but they are same multisets. Okay, so the human actually doing this because human knows the associativity. We don't need to care about the braces, and we know its commutativity. We don't need to care about the positions. Position is okay. And then we have known some maybe cancellation law, okay, but for this case, just associativity and commutativity. And then human will do this on equivalence classes. This is abstract domains. It happens in computer science since 1970s. People developed something called abstract interpretation. Maybe some of you is very famous for static analysis of program analysis. It's based on the Galois connection or Galois insertion to see you want to keep some kind of orders from one space to another space, or concrete to the abstract domain. You keep the orders, and when you map back to from the abstract domain to the concrete domain, some properties is so orders is preserved as well. Okay. This is the most general pattern for what we are doing here. But actually, most of the cases we only care about equivalence classes. If we do something in equivalence classes, it will show there's a proof in the concrete domain, if and only if there's a proof in the abstract domain. And in the abstract domain, the calculation of the proof is easier, just to calculate the equivalence between two multisets. We don't need to manipulate these syntax trees, these tedious, trivial proofs. Okay. So I think it's something we need to do to do these automatically generate these the abstract domains. But how could we do? How could we automatically generate these abstract domains? Actually, these are collapsed structures, as you might see now, from trees and then the multisets and sets and something else, lists. Okay, you can list the structures of this to remove the braces, remove the positions between these elements. So from sets, multisets, lists, and trees, and some trees, subtrees, okay, you can list a collapsed structure sequence, and you can try one of them one by one to see which one you can prove the theorems. The theorem is if and only if theorem. When you prove the theorem automatically, you will show, oh, this structure is exactly what I want. You could find the best one. The best one is the least structure you need. And a lot of algebraic structures will have this kind of structure. Especially for our case, we're manipulating expressions. Expressions just syntax trees. Okay, you can simplify it to list, to multisets, to sets. One you equipped with some rules. These rules, associativity, commutativity, something idempotency, or zero or units. And when you have these rules, you could find this trees. This is abstraction. And induction, I don't have an example here for induction, but my thinking is for most cases, human actually. Let me rephrase this. So a lot of techniques are currently using in computer science. They are exactly induction. It's different from mathematical induction. Like machine learning is trying to generate sort of general patterns from cases using Bayesian, using statistical methods. Anyway, from the observation, you'll find it. Another one is another example is program synthesis. You have some cases for input and output. For example, you have a list and then you got the ranked list or sorted list. You want to synthesize a program to do this task. Okay, this is another induction to observe these cases and try to generate some kind of more general things. Another example is in logical programming. If we know some predicate A and predicate B, this predicate has some relation with each other. Okay, probably they will appear at the same frequencies. Or one is less than another one. You can try to write down A implies B, and see find some supporting from the context, maybe from the human language, from news or from other documents. When you find this, you can use these rules as well. Okay. As example I've shown before, for the mathematical in mathematical applications, especially for progressions like arithmetic progression or geometrical progression, how the great mathematicians find the closed formula, like the n plus 2 plus 2 3 plus n equal to n times n plus 1 over 2. How to find it? This is the capability of induction. We hope the machine can do this as well. But I think interesting thing is we shouldn't learn the basic concepts and definitions. Okay. For example, if we have something like the sequence 2, 4, 6, 8, this kind of thing, you present it to a machine and tells, oh, this is even number, and the machine learning can do it, read all this number into and build a system, build a model to predicate, to predict which number is even or not. So you are given a new number like 32, and the system tells you, oh, this is even number. We think this is a learning of concepts, and it's impossible for good machine learning model to do it because you have infinite natural numbers. Okay, you have to learn the rules. If you haven't produced the rules like n equal to 2 times k, or you produce some kind of procedure or algorithm to calculate, to decide whether a number is even number. If you cannot do this for the machine learning model, you will not produce a correct answer. You can always produce a number that the model never thinks before, and then you fail the model. Okay, a lot of development in computer science are doing this very basic concepts learning, to learn some programs to do ranking, to learn some programs to generate the Fibonacci numbers. I don't think this is necessary. So for induction here, what we mean is for the concepts and definitions, we need to provide these concept definitions by human beings. Let's take the natural number as example, or arithmetic as example. So initially, we only define the natural number, addition, multiplication. That's fine. Let's stop there. And then the machine, because it's an algebraic system, you know this is some kind of binary operators. So you will try a lot of properties, commutativity, associativity, idempotency as you can list. And maybe all the combinations of the expressions of these concepts, all the definitions. And you could use a case analysis to reject most of them, and something will be left, like communication, commutativity, associativity have been left. And then you fit this into the automated system we have developed from A to F. It will tells you this is true, generate the proof automatically. It's true, and then you can use this rule and you put the rule in the environment and use it again. In this step, if you follow this step, you can develop the whole algebraic properties for addition and multiplication. Okay, so I mean, this is just an example. You could extend the idea to other area like set theory or some other theory, but it's not so straightforward. Sometimes you cannot generate so simple algebraic properties. For example, like some formula tautology in propositional logic. Sometimes it's quite long, like P plus Q and Q plus P implies P equals Q. Okay, or the P plus P implies R and Q implies R implies P and Q implies R. Okay, for this kind of thing, you want to generate this formula. It seems that you have infinite space to generate. You could put arbitrary implication and braces and expression or variables there to generate a very long, but most of them are not very useful. We only care about a small set of them. So I think it's achievable. So this is induction. I believe abstraction and induction will become the most innovative part of this project. Okay, I think that's almost everything I want to present here. For something else, I put it into the appendix, including resolution and equivalence checking, example equivalence checking, and model checking, and simplified number. Okay, we'll use it later. Anyway, the last thing we know, but we don't want to touch currently is intuitionistic logic. Say you have to construct programs or evidence to do the proof. It's used in Coq, used in not in Ling or Ho, but in future might be useful as a Martin-Löf type theory things. But we don't want to use it currently. We want to focus on this tiny, small, automated core in future to do some extension. Okay, that's all. Thank you. Any more questions?
Okay, thank you very much. I guess there will be some questions, but let me begin with, first, indeed, we should thank the speaker, and we can put our hands, clapping hands in Zoom. Thank you very much for this talk. So it was interesting to compare, so to say, how we speak about these things and how people practically working and engineers, so to say, view them. But my understanding of the idea of your talk was that you wanted to show us, so to say, some main techniques that you are using in automated or interactive proof.
Yes.
Proof search or calculation or in your work. But what I'm really interested in would be to have some background on what is your problems, let's say more practical problems that you are solving using this. So that's where is it all going? So because, and second question is, of course, so you gave hints that you have this language which allows to represent proofs or calculations somewhat more efficiently than in some other formats that are encountered in these interactive provers. So maybe you can add a few more details about this.
The language, okay. So the first thing is about problems. Actually, I give two examples in front. Finally, we hope we can solve these automatically. Saying the input for our tool, we want to develop a tool actually. So in Huawei,
are actually the working examples that you developed, let's say, automated proof for each of them, essentially, using some of your general techniques that you mentioned.
Yes, exactly. So the techniques we have listed and studied, none of them is new. Okay. It has appeared in everywhere, okay, almost everywhere in history. But some of them could be automated further. We have identified it. So if we implement them in our system, the final goal, the concrete problem is quite like this example. The input of our tool should be the example like this one. The output should be some kind of proofs produced automatically by our tool. That should be human readable, as in Leibniz style, and also machine checkable, that is in the LCF style. That is could be checked at the inference rules. Yeah.
Okay.
And also some kind of application. This is concrete example. Application, and I think one of the applications I have mentioned is design automation here. To see, we're not sure whether the human knowledge or human skills will help some real engineering problem, especially in hardware and software development, the verification problem. Yes, our colleagues in Russia is developing called shallow embedding. is try to use whole logic and also the theorem proving system, trying to do some automation from from software to theorem provers and do it automatically. Okay, that's another way around. But for us, we are focused on some human skills will help identify specific structures or features which could help us to reduce the complexity. That's another round, but both applications we can develop from these. Anyway, by doing this project, by developing this project, we want to benefit other areas, not just mathematical induction or mathematical improving. Okay. The second problem is about the language we are using. Currently, I don't design any specific language. So the language itself is just like this one. It's very simple to say just expression and rule and inference rule. This is a quick prototype. So I'm currently doing the quick prototype. So I will keep the syntax as easy as possible. So just a list of expressions and one expression. For everything we want to do this rule application or evaluation, and we're just using the rule substitution. The rule substitution is easy to be implemented in some functional programming like Haskell. We have invented actually, so it's not really hard. Then the left things is try to use them automatically. How to design this interface, how to define these the automation mechanism. That's a tricky part. I think that we need to develop. Need some time. Maybe several months, maybe one year or something. Okay, but the idea is try to keep this as simple as possible. When I write these typing set forms, that's just really strings. No other things behind it. So it's not a specific programming language. It's just the strings. We manipulate these expressions. Mm-hmm.
Okay, there are some questions asked in the chat. So let me.
Well, may I ask?
I will give you the word next, but before that, question from Sergei Artyomov. Maybe you can ask it, or Chen, you can look into the chat and read it. Do you see any foundational significance in automated deductions? I am thinking about what's these ideas.
Did you say it again? What's the question? Repeat it.
Okay, it's a typical question of a logician, because it asks not about something practical, but about foundational significance. Do you see any foundational significance in automated deduction systems? In particular, about what's these ideas? So this homotopy type theory, maybe you heard about.
Specific foundations of deduction system, yeah. I don't really understand the question, but but I think
by foundational significance, they mean does it should the let's say automated deduction have some impact on the, let's say, foundations of mathematics? That's what.
Okay. Yes, I think okay, I understand now. Mm-hmm. So quite like the questions I asked for Liv on the seminar. So deduction system itself is useless, basically. It's because just to do the validation. We hope these validation could be done automatically by machines to cover the details, to do the checking. Mm-hmm. We call it proof checking or something. It will be very useful for proof checking. Nothing new will be produced from the deduction system. The new things will be produced from the induction and its abstraction. Abstraction is definitely will reduce the complexity, and induction will give something new knowledge, new theorems, new lemmas. Anyway, but from A to E, all of these deduction technologies are foundations actually for other works, for more interesting works. So we hope we could cover these details and automate most of them, at least most of them. Maybe people only need to say a small hint. Say here, we do put case analysis of even or odd number, this kind of hint. When you give this hint, let the computer finish the rest part. And sometimes we don't need to prove everything. as like the whole or some libraries like Cork, people approve everything you know, for rigorous purpose. You prove everything from scratch, from nothing. Okay, that's interesting anyway, but it's not necessary in daily work or in engineering. We think most of things could be considered as laws and rules or axioms. Something has been proved. Okay, and then the most important thing is how to use these laws and rules to do calculation actually. For the rest of the part, we want to leave them to the computers. Okay, if you want a really a proof like the associativity or commutativity is kind of simple, tedious, trivial proofs, you ask the machine to do it. I think machine can do it. Machine definitely can do it now if we implement the whole system. So, so I think that my answer is basically deduction system is not very useful for developing new things, developing new knowledge, but it is necessary for us to do something interesting like induction or developing new system, new knowledge. Okay.
Okay, Nikolai, you like to?
I wanted to ask. Probably
wait
you.
Wait a second. We have not yet finished with the previous question. Next, you are next.
Yeah, no. So basically, it's consistent with what Watsky also thought. So it basically, there are plenty of things which are in mathematics are left as obvious or easy to show. Yeah. And the ambition, your hopes are to provide an exact explicit solutions or some filling all these gaps left unattended or left for the user to fill in. And so you think that a lot of them can be automatically resolved. Okay, I understand. Good.
Yes.
No. Nobody expects the Cork to prove some really new things and to see new directions so far. Or just the other systems too. And by the way, side question, since I'm already here, what about Mizar? Is it still alive, or Mizar, as the Polish call it?
Mizar. Mizar is different. Mizar is I think that is from Automath. I think Mizar is more
is it dead or alive? It's basically, is it dead or alive?
Yeah.
No, that's a question because it's my 20 years ago experience. So that's
it cannot be both dead and alive. So
yeah, maybe in a quantum state, but
no, I think it's still alive. It's still alive.
Yes, still alive. Yeah, still alive. Yes.
Good.
To be honest, I prefer Mizar or Automath style. The Cork style, you have a lot of details. Yeah, and you cannot read it.
Well, it's types. As you mentioned, if you work with types, it's so much harder.
Yes.
Good.
Yes.
Okay. Good luck.
Okay.
Yeah.
Now,
So in any case, what I mean is we want to put the type system aside for a while and focus on this automation to see whether we could help people to solve problem automatically without introducing the complex type system. And if it's necessary, we will bring the type system back into the system. Okay, so maybe the next step to consider type system. Anyway, yeah.
May I just add on to that question? Just very short remark about Unival Foundation. I think they're important exactly for making these automated proofs human readable. No.
Yeah.
Yes. Also for other things. And what you said about Cork, exactly, if you use Cork along with this homotoppical interpretation, that's exactly what helps, to interpret this code in terms of intuitive construction and kind of big, larger concepts.
Exactly. I totally agree. I think finally the proof should be like this, like the leftist style. That's beautiful and easy for people to read. And for the LCF style, the Cork style, okay, it's almost to produce a lot of code and no one will read it again. Okay.
Okay, now please, Sergei Meshviliani.
Well, I want to ask about the achievements of the best provers in mathematics. For example, there is a pool of simple examples. For example, like ordering of a list, sorting of a list, how to prove whether sorting by insertion is equivalent to sorting by merge. So are there provers who do these proofs automatically without human help? And
no, currently no.
Sorry,
Currently
sorry.
no.
The next exams.
Yeah.
A list is reversed twice. Prove that the resulting list is the same as the given list.
Okay.
And the third example, a natural number is coded in binary system by a list of bits. Prove that addition is commutative without help from human. Now, when you run a prover on these problems, there appears a step on which you need to invent a hypothesis.
Yes.
And
exactly.
To reject it or to prove. So invent.
Okay, I think it's clear. So your question is clear. So let now give those questions.
I want to know what are the achievements in this field.
Okay, good.
Okay. Yeah, good. So you mentioned 3 examples. Actually, some of them are appearing in Isabella's introduction tutorial. Okay, like a reversal list is a list itself. Okay, currently there's no theorem prover can finish this kind of proof automatically. No, most of them you still need human help. For our current project, I'll give some examples like the commutativity. I believe for most cases, especially for the list theory I have mentioned, and for these computational structures like trees, binary trees, it could be automatic in several months, I guess. Yeah. So the second question is about the lemmas, to generate lemmas. To generate lemmas is really hard problem. For example, let's look at this lemma C.5. When you produce C.5, you use lemma C.2, C.3, C.4. Actually, there's a lot of research in academia try to derive these lemmas in order to prove the lemma C.5. But I think that direction is a little bit not on the correct way. I think it's a hard problem, definitely. It's a challenging problem. Maybe we could do something from bottom to top to prove C.2, C.3, to do some exploration and produce C.2, C.3, C.4 before C.5. When you prove C.5, you will search in your environment to see whether 2, 3, 4 are there. You can use it. Anyway, this is another way. Well, around. I think with library is bigger and bigger, that means you have more and more laws and rules or properties. You understand better about your computational structure, and you have a better high level automation. So I have no answer to the second question, the lemma derivation, but I think this is a way you could explore.
I have an impression that all the development stays at this one point, and nothing is helpful.
You mean all of these?
I mean the advance in theorem proving. Just this one point. One cannot invent a lemma, and if a program cannot invent a good lemma, it is helpless.
True. Yeah, I agree. For mechanical, I mean, for the tedious trivial proofs, still the automation will be helpful. You could save a lot of work humans are currently doing in Cork or in other theorem provers. But for lemma derivation, definitely there's no good way to deal with currently. Yeah.
Thank you.
Yeah, proofs that do not rely on lemma are called analytic proofs. So certain theorems can be proved analytically,
Yeah.
but not. But okay, there are various problems associated with it.
Yes, for this problem, another engineering solution is to ask a human to give the proof sketch, saying I give the C.2, C.3, C.4, C.5, but I don't know whether they are correct. And then I know roughly the relation between them, and this is the input of the machine, the tool, and the tool will generate the rest part for human. That's an engineering solution. Yeah.
Thank you.
Okay. Anyone else want to ask a question? If not, I would like to make a remark actually concerning something you said at the beginning and also at the end of your talk about this generalization from examples. So you consider this interesting question of whether one can invent, let's say, a proof or a general rule from seeing a number of examples.
Yes.
And also,
This is the same as inventing a lemma.
Yes, quite similar, not exactly the same.
Not quite, but indeed, in general, it's not solvable. But however, people thought about this, and maybe I would like to point you out to a paper, a short note by Matthias Batz. Let me give you the reference. So let me see. Let me try to put it in chat if it is okay. Yes. Okay. I will put in chat the name of the paper title and the journal. So it's he considers the problem of finding a general method to, let's say, generalize a proof of a universal statement from proofs of instances, numerical instances, and considers as a toy example this question related to prime numbers, the Euler proof of prime numbers. So I think it's an interesting note. In fact, Batz was, I think, the only logician who, over the years, seriously considered this problem. So you might be interested in seeing his paper.
Let's find the chat.
Okay,
got it.
Yes.
Yes. Okay. Okay. Good. I'll have a look at the paper. Theory can be science as a generator. Okay. Good.
Okay. Good. Thank you for this talk. Of course, there are many issues here, and the devil is in the details. So, of course, the problems that you mentioned there, sort of by and large, they are well known to all the people.
Yes.
Dealing with not only automated proof, but also in, let's say, structural proof theory. So this is all kind of known. But the interesting part is, of course, that despite difficulties that seem to be unsurmountable, people do continue to solve, to try to achieve the goals, and the progress sometimes is amazing. Like even the problems, for example, as a positive, on the positive note, the success of SAT solving in solving NP-complete problems, which were previously considered to be unsolvable in some sense, in practical sense, but they're now much less unsolvable than they were before. So maybe something like that also awaits in the more general.
May I ask just a brief question, actually about the goal of this kind of research? Because I can see actually two different goals, not necessarily incompatible, but one thing is very natural, is kind of increase the power of say human intellect, right? Even with simple calculator, we may calculate much better than without it. Okay, that's a clear thing. But in your talk, you rather emphasize something different, like automatization, right? We kind of teach machine doing what we are already doing. And that's not exactly the same. So here's the danger: we just become lazy and machine does something for us. So how you exactly understand that's not incompatible. That may be a step, of course, towards something else. But how you think about that? Thank you.
So I think the first thing is try to understand how human do the reasoning, how human could do this, why human can do and machines cannot do. So this project is not only about automation. It's about this understanding. So we want to develop this automation to mimic human reasoning. To say, how could we mimic human reasoning to increase the ability, the capability of machines? If you can do this, that means you at least understand part of human reasoning, how human do the reasoning. So I think the schools are not exactly inconsistent, but sort of a trade-off between both.
Thank you.
Okay, may I dare to add some word to Andrei's question? So,
Yes, please.
as a matter of fact, we need to understand what we compare to what. So currently, maybe you know, maybe you not know that we are living in AI era. AI. So what is AI actually? In many cases, you can find out that AI is just neural network, artificial neural network. And artificial neural network pretend to have some intellectuality, but they are not. They're just trying to learn from some big data, some correlation, which are not visible to maybe to human. And if you compare this so-called intellectuality with what could be even a simplistic ability of teaching machine how to make proofs, it's huge progress if it would be even possible. So it means that so my example of my wording say that you definitely know that the industry needs intellectuality. It's all about intellectuality so far. So, but instead of using the deduction, instead of trying to understand how we really do our simplistic conclusions, industry very fast go to the way when it generate bigger and bigger, huge computational resources, trying to infer any reality from test and train. So we are here, and we need to do something. And I should say that maybe on behalf of Moscow, we are looking for the cooperation for this topic. We need some real progress of science in this direction towards the points on the last slide by Chen, innovation. So whether it's possible or not to find some common approach to those questions. I understand it might seem to be very optimistic. However, as someone, I'm not from mathematical logic at all. I am from algebraic geometry and transformation group theory. But look, 25, 30 years ago, without this boost of Grobner basis, who can say that we can solve any minimal simplistic commutative algebra requirement? It also looked like, very specific. Even for human, it was not very easy to understand whether this expression belongs or doesn't belong to the ideal. Now, and the idea of Grobner basis haven't been seen as very promising. I mean, it's very strange. It's not fully algebraic. However, it really changed the situation. Maybe not fully. May argue that it doesn't solve many problems, indeed, but at least it exists, and it may help sometimes. So this example shows that sometimes we're next to some great discovery, but we even do not understand that it may come true.
So I want to give a concrete example here, just a symbolic addition here. You say it's very simple for human being to do this associativity, commutativity things. We tested it on a machine learning model. It's deep language model. Okay. So the input is a lot of these kind of calculation automatically generated by machines. We do the brute force searching, breadth first searching, We listed them as different variables, a number of variables. If the number is 1, 2, 3, 4, okay, as a testing data set or training data set, and 4, 5, 6, 7, 8, different number of variables as a testing set. Actually, the machine will just memorize what they have seen. So for the variables from 1 to 4, and for the from 4 to 5, they cannot deal with. They don't know what's going on. And this is most powerful language model, BERT model. We use this BERT model as testing. Anyway, they cannot achieve any correct this sequence to the proof for the variables larger they have never seen before. So this is the example to show this actually machine learning is not artificial intelligence, it's artificial idiots. Okay, for the humans actually are doing this very easily to do the substitution, to do symbolic manipulation, but machines cannot do until now. So we have to think about anyway how to ask machine to do it. For symbolic computation, it's okay, but for the neural, not this case.
Okay, well, on this both optimistic and pessimistic note, we are going to close our seminar for today, and hopefully we will have more of these kind of practice-oriented talks in the future. So thank you very much for